Let me first thank the organizers to bring us all here for this very interesting workshop. I'm already learned a lot this morning. And I'm going, as Maria said, I'm going to continue the discussion from the morning. And that is going to be about, I would say, non-Kitaev physics in Kitaev materials. So basically about magnetic orders in, my particular topic will be magnetic order in hyperhoneycomb magnet beta iridate and its evolution in a magnetic field. And what we learned this morning that in principle that can be extrapolated for other compound of this series. So what I'm going to talk is mainly in these three papers, and the big part of my talk is on this last very recent archive. And this work was done with my student Min-Kun Lee and with Yanis Roussouhatzakis, who is now in Loughborough University in the UK. Like every fairy tale, everything started with the model, and the model was introduced today already. And this model is the Kitaev model. Okay? So Lucas did 1 minute excellent introduction, so I don't need to do it. And what is amazing about this model, that this model is exactly solvable in 2D, but it's also exactly solvable in various three-dimensional lattices. And the only thing what you need is free coordination. And if the Mother Nature would be very kind, and we would really have materials which would realize this model exactly without any other perturbative term, then we'll have many different materials with spin-liquid ground state. But unfortunately, it's not the case, and there are some additional interactions which break this kind of simple picture. Though I still believe, I'm belonging to that people who still believe that in experiment we can still see some remnants of the Kitaev spin liquid. The only question is how to look for this. But that's not the topic of my talk today. And another important thing, once again, unfortunately, George didn't manage to come today, is that the Kitaev model appeared to be realizable. Because at the moment when Kitaev proposed the model, it looked like artificial, beautiful, theoretical model. And the work by George and Ginyard Khaliulin actually showed that there is a whole class of materials in which this model can be realized. And what you actually need, you need some degrees of freedom which could interact with this anisotropic interaction. And for that, you need strong spin-orbit coupling. And originally, they suggest that iridates can be good candidates. Compounds with rhodium can also be good candidate. And ruthenium chloride showed that ruthenium materials is also like excellent candidate for Kitaev physics. And the reason why most of the compound order is actually that in all real materials, and that was already shown in this paper, Kitaev interaction, the dominant Kitaev interaction, comes with some other perturbative term, and they can break this spin-liquid ground state. Oops, sorry. And okay, so this was already shown that nowadays there are many candidate materials, and among them are iridates, sodium iridate. That was the first compound which was studied, and then alpha, beta, gamma iridates. Alpha iridate is two-dimensional, ruthenium chloride. And the only compound which doesn't order so far is the lithium iridate intercalated by hydrogen, and that compound was synthesized in Hidetakage's group. And in this material, disorder plays a very important role. And maybe disorder is of that kind that actually Kitaev physics is still realized in this material. And then three-dimensional materials, so beta iridate and gamma iridate, both of them are very interesting and can show, in nature they have dominant Kitaev interaction. So the focus of my talk is the complex magnetism in beta iridate, and you see that recently it was quite a lot of interest to this material. Okay, so despite that you heard about this material this morning, let me briefly summarize what are the experimental facts. At the paper of the group of Radu Caldea in 2014, the magnetic structure of this compound has been analyzed, and it was shown that below 37 Kelvin, this incommensurate counter-rotated spiral is realized. And if you look here, this is AC plane, then you need to look to this XY zigzag chain, and this order sits on this zigzag. So basically, you can take each of these zigzag, and the top spins are rotating in one direction, and the bottom spins are rotating in another direction. And they also found what is the irreducible representation describing the static structure factor. Okay? So this is the first experimental result about this compound. Then the group of James analysts analyzed this in more details, and what they found that if you apply magnetic field, then this incommensurate order is very fragile. So they first applied the magnetic field along B direction, and they found that this incommensurate order is destroyed at the field around 2.8 Tesla. So this field is very low, and basically that showed that maybe when this order is destroyed, there is some space for spin liquid state in the same way as people are discussing in the ruthenium chloride. They also found something interesting, which they call intensity sum rule. So let me explain what it is. So a part of this incommensurate order, they also found that in the applied magnetic field, there is a zigzag order. So this is a uniform order which is growing with the field. And this zigzag order is along A. But at zero field, this order is very tiny, and that's probably the reason why it was not observed, this uniform order was not observed in the zero field experiment of Radu Caldea's group. So the suggestion is that there are two coexisting orders. One is Q equals 0 order, which is the zigzag order, and the incommensurate order. And this incommensurate order here is shown by green. So one, the spectral weight, so what we see here in the field is how the spectral weight is transferred from the incommensurate order to this zigzag order. Okay? So in the magnetization versus field, once again, the field is along B direction. What was shown that if the temperature is below Néel temperature, then magnetization shows a certain kink at H star, and this H star is 2.8 Tesla.
These two types of order coexist in the same bulk of material? Or
in the same, no, it coexists in the same bulk of material, and therefore later I will show how this intertwining of these two orders can appear in our model. So, and then recently, so actually at the first experiment, they only measure the response in the field up to 7 Tesla, and they see the kink when the field was applied along B direction, but the magnetization along A and C direction remain without any significant changes. Okay? And this is the material in which susceptibility is highly anisotropic in the field. It was a recent new set of experiment which actually showed that, once again, they went already to the field up to 14 Tesla, that the magnetization process and the response of the system when the field is applied along A, B, and C direction is small, and the significant changes and in the magnetic structure at the very low field was only observed in when the field was applied along B direction. These are the data from recent publication from, again, James Analytics group. And they also see, when they measure some specific heat, they also see some features around 100 Kelvin, and they see some interesting hysteresis in the magnetization around 100 Kelvin again. But I'm not going to talk about this. So I don't think that these observations are understood or repeated by other experimental groups so far. I will say what we think about this, but in any case, we don't have a good explanation for that.
But one of that is the Néel temperature, or?
No, the Néel temperature is this 37 Kelvin. And basically, they see some features of another thermodynamic transition at 100 Kelvin. And this transition is very weak. It's only observed in the very, very tiny magnetic field around 100 oersted. And when you go to the field around 1 Tesla, all these features completely washed out and disappear. So these features are very sensitive to the magnetic field, so not completely clear where they are coming from. The model, so the starting model which was first proposed to describe this compound is this general JK gamma model, which was discussed today, where K is the Kitaev interaction, J is the Heisenberg interaction, and gamma is this isotropic exchange, which you explained already. So it's basically if you have a Z bond, the interaction is XY plus YX. And here we only take the nearest neighbor interaction. So we are aware that in principle, one can add further neighbors interaction, but let's focus on this model and let's try to see if this model is sufficient to explain the majority of the experimental data. And this is the classical phase diagram. And in this first paper by Yong by Kim, it was shown that the phase space for this incommensurate order sits here. And parameterization, again, J is sine. So what is going when you go inside is the gamma interaction. Gamma is 0 on the boundary, and gamma is increasing when we go towards the center. And phi equal to 0 corresponds to the Heisenberg model. This is Kitaev model. This is ferromagnetic Heisenberg model and ferromagnetic Kitaev model. So this is this region, and our work last year, we showed that, in fact, inside this region, there are two different orders which has similar symmetry, the gamma dominant state and the Kitaev interaction dominant state, and experimental results are more consistent with what we call K state. Okay, so this where we focus, and in this region, Kitaev interaction is ferromagnetic, gamma interaction is ferromagnetic, and Heisenberg interaction is the smallest interaction, and it is antiferromagnetic. So before I discuss how we obtain this incommensurate spiral from all these orders, classical orders, which sit here, let's consider this special line, phi equal 3 pi over 2, when Heisenberg interaction is equal to 0. So in this case, let's take the elementary unit of all these lattices. So we have one X, one Y, and one Z bond connected to the side. And we start with some spin inside S0. And then we try to satisfy both gamma and Kitaev interaction along each of these bonds. For example, if we go along X bond and the gamma interaction on this bond is positive, so comes with sign plus, what we do, we kept X component of spin the same, and we switch Z and Y components of the spin. So if, for example, we go along the Z bond, then we keep Z component and switch Y and X. And if we go along Y bond, because the local surrounding of this ion is different here, here the gamma interaction comes with a negative sign, with sign minus, and that means that along this bond, on the spin 2, we keep the same component, same Y component, and switch Z and X component of spin, and also add sign minus. So this is the construction, and by this construction, we can cover the whole lattice, and we can compute what is the energy. And what is important, that the energy of this covering actually corresponds to the minimum of energy obtained with Lattinger-Stieser. So it's really fit the low bound of energy, and therefore it describes the ground state. But now the degeneracy which we have along this line is the degeneracy associated with the direction of the initial central spin S0, because it can point anywhere, and therefore we have continuous degeneracy of the states. Please.
Before we go further, a naive question. Is there any empirical, experimental, or just hand-waving argument about why do you limit yourself with these particular 3 parameters, while symmetry allows many more? Any recipe of how you were selecting just these three?
So I think from ab initio calculation, at least it follows that these are, so the gamma interaction and the Kitaev interaction are two dominant interactions. Okay, so I think everybody agree from the experiment and from ab initio calculation that these are the dominant interactions. Then in order to stabilize this state, you need something else, because if you have just these two interactions, then you are on this line. And on this line, you have the family of continuously degenerate states. So you can add J. So we add the small value of antiferromagnetic J, which can select the state which mimic this incommensurate spiral. You can add J free or gamma prime and so on. You can add any small, any other small interaction which from this family of degenerate state along this line will select the state which has.
There is good evidence that these three are larger than everything else.
There's a good evidence that these two are larger than anything else. And J interaction, you will see that in our approach, J is very, very small. Okay.
So just a follow-up, just to understand better. So you're saying that there are ab initio calculations of, let's say, a large variety or the full class of spin-spin interaction in this system, and calculation clearly indicates that the Kitaev and the J1 are the dominant terms.
So I don't know if how about the general. So I think there is a calculation of Yom by Kim group. There is calculation from Roser Valenti, and I don't know if there are others.
No,
so I think these two.
And Dresden also.
Yeah.
Dresden also they did.
The quantum chemistry, yes, and quantum chemistry. So,
Yeah,
so
the
from
question
this.
is, I mean, these calculations have, let's say, explore the full spin-spin configuration space and extracted these as a dominant.
Most, let's say most of the space. The space is huge, but you go up to certain, up to, yes. Okay, so what I want to say next, that along this line there is a special point, in all this point there is always this point with the hidden symmetry, which Ginyat Haleulin and George and E.G. Chalupka was advocating. And basically this is this point, SO3 point here. And this is the point where the Kitaev interaction equal to gamma. And in each of these XY chain, you have 6 sublattice, and you can perform the 6 sublattice transformation. You can rotate the couplings of your Hamiltonian, and you can show that you can map it to the Heisenberg Hamiltonian, and therefore this particular point has continuous symmetry and gapless spin wave excitation.
You mean for given bond, Z is along the bond to perpendicular to the bond?
Say it again, I didn't say.
When you write Hamiltonian,
Yes?
you for each bond you have different form of the Hamiltonian.
Yes.
And Z it is along the bond Z direction.
Z direction, so basically you have XY chains, so this XY chain, and they are connected by the Z bonds. But because this is hyperhoneycomb lattice, so in the hyperhoneycomb lattice, you cut along each Z bond, and next XY chain, so let me go back maybe here.
No, I mean for given pair of atoms, what
So
is
for-
local coordinate system for which this Hamiltonian belongs?
So for each pair of atoms, I can say, okay, red is my X bond, therefore my Kitaev interaction is XX. Then my gamma interaction along this bond is YZ plus ZY, and there is a Heisenberg interaction. And Z bond is this one, okay? And basically along each Z bond you cut, and then next XY bond is rotated by 90 degrees. That's how you can understand this structure, starting from the
Maybe
simple
more
honeycomb.
easy, is it correct that if I define local coordinate system for each bond along the bond would be Z in standard
Yes,
type?
yes,
Okay.
yes, yes.
No, it's the red axis, the cubic one.
Exactly.
I mean, you just choose the another local notation. You can,
Exactly.
so, I mean, in principle, in the local, you can put Z tilde and call each bond Z tilde and just do the proper rotation. Okay. Okay. So what I want to say that there is this special point where the excitations are So this is the Heidelberg. Okay, so what was our main idea? Our main idea was to look in this phase space where in principle the state can be and find a commensurate state, because once we have a commensurate state we can do all the calculation. We have a finite unit cell, we can do spin waves, we can perform all the analysis. So we were trying to find what is the minimum unit cell commensurate state which has the proper symmetry. And we found this 2/3 state which has all the proper characteristics in the K dominant state. So in these particular states, they differ from the real experimental state that it's commensurate, and it's not exactly this Q which was observed in the experiment, but the static structure factor for this order is the same. And the order which it's described, so basically this order is described along this zigzag chain, red and green chain. So you can see that we need to have 3 sublattices, and on the bottom of this chain we have sites A, B, C, A, B, C. It's almost ideal 120-degree structure, but on the top the order is CBA, CBA, and from that you see that rotation is opposite. So basically that's described the counter-rotated state. So however, in this state, it's not only this finite Q state, but it coexists, it's at the same time, it's intertwined with the uniform order with Q equals 0. And these are the components of this order. So in our unit cell, in the hyperhoneycomb lattice, we have 4 sites. And in these 4 sites, basically this letter A, C, F, G, these vectors describe what is the proper sign of the order coming from this different side of the primitive unit cell. And now you can see here, if this A, B, and C are the sublattices, I mean these orthorhombic unit vectors, then the order which we have, this A, B, C, is almost 120 degrees, but it's canting. And this canting is described by this uniform order. It's canting towards A-axis, and it's canting a little bit out of plane. So, and this canting is described by these 2 components of the static structure factor. Okay, so the idea is that now we look to the behavior of this material under magnetic field along different direction, and we show that we can describe it in the unified matter. Okay. Okay. Sorry. Okay. Maybe it was not important, so it was just no, it was important. Okay. So what was important here, that because of this particular structure in this material, so this is what we add is the magnetic field. The G factor is anisotropic. G factor has these diagonal elements which we call AA, BB, CC, because that's along the orthorhombic unit vectors. And JAB is not the plane perpendicular to C, but this is this off-diagonal component. And what is important that this off-diagonal component are coming with the prefactor +1 or -1, depending on which zigzag chain we are considering. Okay, so what is important? So everything what I'm going to describe based on the symmetries. We need to perform the symmetry analysis, and the 3 main symmetries apart the translation symmetry, which is broken by this commensurate state, finite Q state, is this rotational symmetry. So in this lattice, we have this free pi rotation symmetry, the rotation along B, C, and A axis. And let me show like a simple example. If we perform this pi rotation along C axis, then we are mapping X bond to Y bond along the same chain. And this is the symmetry of the Hamiltonian. So C2, C is the symmetry of the lattice, but in order to have the symmetry of the Hamiltonian, we need to perform a corresponding rotation in the spin space. Because in these materials, in all these Kitaev materials, the spin space and lattice space are coupled by strong spin-orbit coupling. So in the same way, C2A symmetry, so you can rotate by pi along these axes, it will map this X bond to the Y prime bond of the next zigzag chain, with corresponding operation on the spins. And there is similar C2B symmetry, which map X bond to X prime, so this red to this dash red, and this green to this dash red. So now when we apply magnetic field, some of the symmetry will be broken. And depending which symmetries are broken, then that would determine what kind of magnetization process we will have. So briefly, what I want to say that this intensity sum rule is satisfied in all field direction, and this is basically the consequences of the local spin length constraint in the classical analysis. What is important? Let's consider this magnetization process in the B field. So what we see, and we already discussed that in the low field, these lines correspond to the component of the static structure factor for commensurate order. And you see that all three of them goes to 0 at this critical field HB star, which is 2.8 Tesla. And we see that this zigzag component, yes, the zigzag, 5 minutes?
Yes.
Okay, so these zigzag components are growing, and when you see that when this order is killed, actually these zigzag components are not 0. And here, let me briefly show how this magnetization process is happening. So you first see this 6 sublattice structure, and then above this H star field, you see that there is a 2 structure, and the field is growing and growing, growing and growing, but you don't achieve even classical fully polarized state. I'm not speaking about quantum mechanically. So these zigzag components are very, very robust. So another important thing that when above this H star, the spin lies in the AB plane, so this zigzag is fixed by the field. This is the similar process in A field. What you need to see that the main difference is that this H star is around 100 Tesla. So it's significantly larger than that. And then you see again that there is this polarization process. And finally, you have this 2 sublattice structure. And once again, I mean, you look to the field, it's a huge field, and it's still not fully polarized. So the stability of these zigzag Q-0 phases in the field is very strong. This is very different, because in this case, since not all the symmetries are broken at the first transition H star, there is a room for the second transition. And here the situation is different. You first have, again, 6 sublattice here, but then when you go to the 2 sublattice structure, the plane where you have this zigzag is not fixed by the field, and it's changing with the field. So what is important, I didn't say before, that all these critical fields, they scales with the parameters. Let me go quickly here. So when we have, I will skip. So the fact that the B field, the critical field along B direction is small, actually tell us, because this is proportional only to Heisenberg interaction in this model, it tells us about the smallness of the J interaction. So from this, we can extract that J is around 0.4 millielectron volt in order to produce this critical field observed experimentally. So when we go to, so basically each of the field contains the information about the coupling. And what is important that when we have the field along C direction, then both fields are a combination of J and gamma. But for example, since we do have around 45 Tesla, we do have a second transition. And when we reach the fully polarized state, that can give us the estimate of gamma. And 44, 45 Tesla, we believe, is a reachable field. So this critical behavior at different fields give us information about the couplings in the system. So this is basically the picture. In all these 3 different cases, we have 6 sublattice low field phase, we have 2 sublattice high field phase, and what we need to check which symmetries are broken in the field applied along different directions. And the stability of the zigzag orders, if you do the Landau expansion of the energy, you see that this component of the static structure factor, which correspond to the zigzag order, are coupled or with this gamma. And since gamma is a rather large interaction, that actually tells you why these zigzag components are stable at very, very large field, significantly larger than even Kitaev interaction. So this is the phase diagram, which summarizes what I just said, obtained with Monte Carlo. So we also, because we have this commensurate state, we can compute spin waves. This is just the linear spin waves. But what is interesting is to see how this is dynamical structure factor, how is evolution of dynamical structure factor in magnetic field. So what you see here is the following. So this 2/3, this is shown in the units of Q corresponding to orthorhombic unit cell. So this 2/3, this intensity at 2/3 corresponds to this incommensurate order. In our case, it's 2/3 order. And you see that our uniform component, which correspond to Q equals 0, they are gapped. So this gap is significantly larger than that. And now let me show, oops. So the field is changing, the field is along B direction, and you see how slowly is this process is happening and how flat is, I mean, this is already very huge, but when it turns, this low energy branch is very, very flat. And I think that's also explained the behavior of, this is the gap. I don't have time to talk about this, but one can extract how the gap is behaving, and that is consistent with NMR. This is magnetization. Once again, let me skip this. The only thing I want to say that, I understand, so just like two more minutes. So what I want to say that because when you compute, because of this G factor, the combination of anisotropic interaction and G factor give you magnetization, which often, when the field is along A and the C direction, it gives the component of magnetization which is perpendicular to magnetic field, and therefore it gives rise to the final torque. This is the data, so the orange is the classical solution, and the blue is what we get when we take the linear spin wave correction. So quantum fluctuation on the linear spin wave level is taken into account. And you see that the torque when you have a field along A direction is significantly smaller than the field is along C direction, and torque is identically 0 when the field is along B. Kim will be talking about this, but in our analysis, we can also do all this angular dependence on the torque. And that's, again, it's a very similar discussion that Steve was talking today, this paper about rotating current. So I think all this physics is kind of connected. And what I wanted to say here, that in principle, all these particular features of the torque can be obtained without going to exotic features, basically from this anisotropic nature of magnetic order and magnetization processes. Okay, this is just the comparison, and this is conclusion. So the main idea which we follow in all these analyses, that symmetry is important, and that this period-free order, this commensurate order, can mimic this incommensurate order. So in reality, in the experiment, you take this commensurate order and you have a twisting of this commensurate order. And then what we believe, why we believe it's important to study the magnetic response in different field direction, because by this we can probably fix the parameters of the model better, give us additional information about parameters of the model. Thank you very much for your attention.